Hello there. In this short video lecture, I will introduce you to the concept of excitability, and we'll also see how membrane potentials can be recorded. Now, all cells, organisms, and of course people respond to changes. The ability to respond to changes actually depends on the ability to sense changes in the first place, and then to change appropriately in the context of the changes that have happened in the external environment. Now, excitability is a key feature of cells that allows cells to respond adaptively in a particular way. What is this particular way? At the cellular level, operationally, excitability can be defined as the ability of cell membrane to respond to stimuli with electrical changes in their membranes. Now, it turns out that almost all cells, in almost all cells, the membrane is charged. What do we mean when we say the membrane is charged? The membrane has a potential difference across it. There is a separation of charges. There is an electrical potential across the membrane, and this potential difference changes. And one of the key features of excitable cells is that they respond to stimuli with substantial changes in the electrical potential across the membranes. Therefore, understanding membrane potentials is the key to understanding excitability. This ability of some cells to respond with changes in their membrane potential plays a key role in their ability to function as signaling cells like neurons, or contractile cells like muscle cells, or for that matter, in a vast majority of cells, the changes in their cell membrane potential is associated with functional changes, and therefore the way in which these cells respond to stimuli, respond to changes in the external environment. To understand excitability, let's begin with methods to record membrane potentials. Now, membrane potentials can be recorded using this kind of a experimental setup, where you have a voltmeter, a sensitive, sophisticated voltmeter, which of course would have a positive terminal and a negative terminal, and one could attach a narrow-tipped electrode, a recording electrode, to the positive terminal, and a fine, narrow-tipped reference electrode to the negative terminal. You can have a good microscope under which you can focus and visualize the cell that you want to record the membrane potentials from, and under this visual guidance one could get the electrodes close to the cell, and in fact you could attempt impaling the cell, penetrating the cell, and entering the cell with the electrode, and therefore you would be able to measure the potential differences across the cell membrane. Now, of course, one would want to display these changes, one would want to display these membrane potentials, and you can have a chart type of recorder or a display in which you would have time on the x-axis, and on the y-axis you would have the potential difference, and since these differences are quite small, millivolts would be suitable units for displaying and recording these membrane potentials. This is the isoelectric line, the zero line, and if the signal goes above the zero line, you would be recording a positive membrane potential, and if the signal goes below the zero line, you will be recording a negative membrane potential. So this would be the basic setup that is required to record membrane potentials, and let us say that under visual guidance you gradually bring the recording electrode and the reference electrode to a point close to the cell membrane, and in such a situation what you would observe, what the voltmeter would record, is essentially a flat line. at 0. What this means is that both the recording and the reference electrodes are exposed to the same potential, and therefore there is no potential difference between these electrodes. Now, if you were to gradually, gently lower the recording electrode into the cell, impale it so that the tip lies now within the cell, then as the electrode dips into the cell, as it enters the cell, the voltmeter would record a sudden drop in the membrane potential. And as long as the recording electrode is within the cell, the voltmeter would record a more or less stable, flat membrane potential, but which is below the 0 line. In other words, it records a negative membrane potential. Now, what this means is that the inner side of the membrane, the interior of the cell, is negatively charged, or is at a negative electrical potential compared to the external side of the membrane, to the exterior of the cell. Now, if you were to pull the electrode out again as it leaves the cell, the voltmeter would record a potential that is back to 0. That means again the two electrodes are exposed to the same potential, and therefore there is no potential difference. So, this kind of an experiment demonstrates the fact that cell membranes are charged. There is a separation of charge. There are more negative charges on the internal side, on the inner side, compared to the outer side. And therefore, in many cells, in most cells in fact, there is a negative membrane potential. Now, this of course assumes that these are cells which are not electrically active, which are quiescent, which are at rest, and therefore this would be the resting membrane potential, a negative membrane potential in a resting cell. So, to formally define membrane potential can be defined as the electrical potential difference across the cell membrane. Therefore, it would be the potential inside minus the potential outside. And what one needs to remember is that membrane potential can be truly measured only with intracellular electrode. The membrane potential of a cell which is electrically quiescent, a cell which is at rest, is referred to as the resting membrane potential, and almost all cells that have been recorded from display a negative resting membrane potential. However, the magnitude of the membrane potential varies from cell type to cell type. For instance, epithelial cells, skin cells, they have a resting membrane potential of about minus 40 millivolts. Typically, neurons, spinal motor neurons have a resting membrane potential of minus 70 millivolts. Skeletal muscle cells and cardiac muscle cells have even more negative membrane potential, resting membrane potential at around minus 90 millivolts. So, to summarize, the cell membranes have a charge separation. They are polarized. Now, this raises some interesting questions like, how does a membrane become polarized? How does this inside negativity in the resting state develop? What are the implications of such a charged membrane? So, these are some of the questions that we'll explore in the subsequent videos and exercises. Thank you for listening in.